Hey, everybody. We're going to start in Chapter 2, Section 1. And we're going to talk about instantaneous rates of change and tangent lines and how they apply velocities. So let's start. Suppose we drop a tomato from the top of a 100-foot building and time its fall. So basically we have this over here. And there's a little guy at the top, he drops a tomato, and here's our table, and it tells us how many seconds has elapsed and where it is as far as the height is concerned. So some questions are really easy to answer just from this table. For example, A, how long did it take for the tomato to drop 100 feet? Well, it started here at 100 and it dropped to 0. So it took 2.5 seconds the whole time. Okay. It says, how far did the tomato fall during the first second? So here's our first second. And the tomato fell 100 minus 84 feet, which is 16 feet, because the height above the ground was 100. Now the height above ground at 1 second is 84. So that's how you would know to subtract them. How far did the tomato fall during the last second? Well, the last second would be between here and here. So in the last second, we fell 64 feet, from 64 to 0. I'll just write 64 minus 0, which equals 64 feet. And then D says, how far did the tomato fall between t equals 0.5 and t equals 1? So t equals 0.5, t equals 1. Again, we just subtract them. 96 minus 84, which is 12 feet. So those were all pretty easy. Once we had the table, there was really nothing to it, right? So let's continue on. It says some other questions require a little calculation. That required very little calculation. But let's say I want to know the average velocity of the tomato during the fall. Distance equals rate times time. We've used that before, okay? And if I want to know my rate is the same as my velocity. So rate here is equal to velocity. So to find that, I could say R is equal to the distance divided by time, because those are the two things we have. We have the distance, we have the time. So what was the average velocity of the tomato during the fall? During the whole fall, well, we would say the average, I'm just going to abbreviate, average velocity, okay, of the tomato during this fall is the same as the slope of the line from wherever we start to wherever we end. This wants it for the entire time the tomato is falling. So we're going to say time is our X value and height is our Y value. Now, look how important making sure that you have the right X's and Y's, or inputs and outputs, because if I say this is 0.1 and this is 0.2, I'm going to have y2, which is 0, minus y1 divided by x2 minus x1. So this becomes negative 100 divided by 2.5, which is equal to, so my answer is negative 40, and it's in feet per second. Okay. Now, F, what was the average velocity between time t equals 1 and t equals 2 seconds? Again, our average velocity is still equal to the slope. And let's get our new x and y values, or input and output values, whichever you prefer. So let's see, t equals 1, we have 1 comma 84, and t equals 2, we have 2 comma 36. So let's see what we get. Again, I'll call this point 1 and I'll call this point 2. So I have y2 minus y1 divided by x2 minus x1. This gives me negative 48 over 1, which is equal to negative 48 still feet per second. Okay. Some questions are a little more difficult to answer. How fast was the tomato falling 1 second after it was dropped? Well, we really can't answer that. We don't have enough information. So what we're going to do, since we want to know at t equals 1 second, we can only estimate. So we can say we have these 3 points. If we go to 0.5, we have 0.596. We have 1.084. And the last one at 1.5, we have 64. So let's use our top 2 numbers and see how fast the average velocity was between 0.5 and 1. So that's going to equal, so 0.5, so I'll use this as 1 and this is 2. So I have y2 minus y1 divided by x2 minus x1. And we end up with negative 12 divided by 0.5, which is the same as negative 24 feet per second. Okay, so that takes care of my average velocity between 0.5 and 1. Now let's see what our average velocity is between 1 and 1.5. Because those are really the closest points we have. So that's the only thing we can do to estimate it. So now I'm going to switch these two. I'll make this 1 and this 2. So I have y2 minus y1 divided by x2 minus x1. And we have negative 20. Is it 84? 84 and 64. Okay, negative 20 divided by 0.5, which is equal to negative 40 feet per second. So I have these two answers that are pretty far apart, actually. And we know that the average rate of change over, or the average velocity over the entire time the tomato was falling was negative 40 seconds. And we know that it's speeding up a little bit in the negative direction as it falls, which makes sense. Gravity's pulling, so there's an acceleration pulling down, and that's why our values are negative, because we're dropping things. If the object was going up, we would have a positive velocity. So it's hard to say what it's going to be, but it's going to be somewhere between those two numbers. Okay, that's really the best we can do, is just take the average. All right, so now let's say we have the average rate of change versus instantaneous rate of change. Well, the average rate of change, we said, if we have a graph, let's say this is our graph, and we know that if I pick a point here and I pick a point here, I can connect those 2 points with a line. Okay, so those 2 points are now connected with a line, and I can find the average rate of change. I'm going to say the average rate of change is average rate of change. So arc is going to be the average rate of change. But what if I want to know the value exactly at the top? Let's say I want to know the value right here at the vertex of this parabola. Well, we call that line the tangent line. The tangent line actually goes through that one point and that one point only. Because remember, we're looking for the rate of change exactly at one point. All right, so I would have to say, there it is. Notice that it is not anywhere near what my secant line rate of change is. So here, my average rate of change is this line. It has a negative slope. And it's really just the average rate of change between this point we'll call A and this point we can call B. Okay. But if I want to know my instantaneous rate of change at the vertex, look at that. The tangent line is actually pretty easy to tell, because the slope of this line is equal to 0. So how would we find it? Well, we could keep moving this point right here closer and closer and closer and closer. And eventually we could say it's so close that they're almost the same point. And that's how we can find our instantaneous rate of change, or our instantaneous velocity. Okay? And if it was velocity, this would have to be time, and this would have to be distance, because we know that velocity is, I've already shown you, r is equal to the distance divided by the time. And the slope is equal to the distance divided by the time, right? So we can see that the velocity and the slope are the same. Okay? And what we have here with this red line, notice it's only hitting that curve in one place. So I want you to notice it's only hitting that curve in one place, right where we said we wanted. This is called the tangent line. If you want to find the tangent line, you're finding the instantaneous rate of change. If you find the slope of the secant line, these are secant lines. Secant lines hit the curve in more than one place. And we can find the slope of that because it's between two different points. Just remember, tangent line, like if you have a circle, if I draw a circle, where is a tangent line? A tangent line can't go through the circle. The tangent line can only hit that point in one place. That means that this is a tangent line and this is a tangent line. And there's infinitely many tangent lines on that circle. Okay, it's like skimming over the top of it. Okay, and that's what this figure here also is doing. The instantaneous velocity at a particular time and height, so that's basically saying x and y on the graph, is the slope of the tangent line. And I'm going to add in here, as a preview, the derivative. That's what the derivative is. It's the slope of the tangent line. Now, it can be the slope of the tangent line at a point, and then we have to know what value we're plugging in, or it can be the slope of the tangent line as a function, y equals mx plus b. If I want to know the equation for the tangent line, this right here would be the derivative. So the derivative is really important. It's basically most of what we're going to learn this term, besides what we did before, which was review. And so I want you to get the idea of what we're doing, okay? And this graph right here is a graph of the tomato falling off the roof. We start here at 100. We ended 0 at 2.5 seconds. And those are all the different points and all the different times along the way. And if you notice, we never actually found the slope of the tangent line, but we can when we start to learn how to find derivatives, okay? So here we have the average velocity is equal to the change in position divided by the change in time, which is the slope of the secant line through 2 points, exactly what we said. Instantaneous velocity is the slope of the line tangent to the graph, which is what we have said. Here, what we're going to do is we're going to connect dots. And when we connect them, we're going to see, are we going to see instantaneous or average rates of change? Well, if I connect 2 dots together, any 2 dots, I'm finding the average because I'm finding the secant line. If I ever can find it at 1 dot, that's the instantaneous, okay? Okay, so I did take some time. I know I cut that all out, the lines for you. So let me explain what I did. So first thing is I connected every dot to this dot at 1. And what you'll notice is that the closer the dots get together, the sooner it will become the tangent line. I can't really exactly draw the tangent line right now. I could take a guess. So tangent lines, What I did here is I drew lines between each one of these points as long as they connected to the point at 1. So the red line goes through this point. The blue line goes through this point. The green line goes through this point. And you can see that as I get closer to the value at 1, the slopes of the lines are changing little by little. The closer I get, the closer we'll get to the tangent line. So I think that's basically what this says. Notice as the interval gets smaller and smaller, the secant line got closer to the tangent line, and its slope got closer to the slope of the tangent line. That's good news, since we already know how to find the slope of the secant line. But it's going to be even better news because we're going to learn how to find the slope of the tangent line. Okay, so let's get this example, then we'll be done with 2.1. The graph of y equals g of x is right here, in red. At what values of x does the graph of y equals g of x below have horizontal tangent lines? So first, let's make it a little bigger, okay? And a horizontal tangent line would be a line where the slope equals 0. Basically, you can see now that when I have a horizontal tangent line, this is something, again, like a preview, is that at what we call local, maximum, and minimum values, or we could say where the graph turns, that is where our horizontal tangent line are located. There may be other places, but for now, I think that's sufficient. This is a maximum value, but only in a certain interval. So it depends on the interval as far as where your horizontal lines are. So this would be a local min, but then why is it called local? Because I also have a minimum value here as well. And I also have a maximum value here as well. Okay, so that's why we call them local. The other word would be absolute, which means it's the biggest. But we don't have that. We have a lot of local ones right now. So anyway, that concludes 2.1. Thank you for watching, and I will see you at 2.2.